Yeah, dear viewers, today we are going to be discussing the mass spring damper system, and this is a very important model that we use in a number of applications. One is in vibration isolation, which we use it to reduce vibrations in buildings, bridges, and other structures. In suspension systems, the automotive suspension systems use the mass spring damper system principles to improve ride comfort and stability. In aerospace, we also use it in the aircraft and spacecrafts to, first of all, control vibrations and improve stability. In robotics, we also use it to improve stability and precision. We use it in structural control to control structural responses to external loads such as wind or earthquakes. So it is a very crucial and fundamental model. So the question says a mass is attached to a spring of stiffness K and a damper with coefficient C. A horizontal force F of T is applied to the mass. Use the numerical values. Mass is 2 kilograms, C is 5 Newton second per meter, and the spring stiffness is K, which is equal to 20 Newton per meter. The tasks are to derive the equation of motion and show the transfer function from force to displacement, calculate the natural frequency, omega n, and damping ratio zeta, then to classify the system whether it is underdamped, critically damped, or overdamped, and C, to find x of s for a unit step force, and then we shall use MATLAB to show the response due to the step input, and we shall give our comment at the end. So let's right away look at the solution to this problem. So we are told that mass is 2 kilograms, the K is 20 Newton per meter, and then you see the damper coefficient or damping coefficient is 5 Newton second per meter. So we have to look at the model like this. This is the mass spring damper. Now, first of all, we have a damper. So this is going to be our C, and this is going to be our K. So the damping ratio or coefficient is this, and this is our spring. So when you apply a force, either by compressing or by extending, like this force, the way it is doing, we shall have a displacement x. So x of t is actually going to be displacement. Now you realize that when you have displacement, we shall end up also talking about the x of t, the x of t by dt. This is going to be velocity. You know, velocity is the rate of change of displacement with time. Then if we have the 2x of t, okay, then we also have by the t2, then this is going to be acceleration. Very important concept. So what do we begin with? We shall again redraw the way how these forces are going to be realized. So we shall have a force due to this, let me call it Fc, and then the returning force, let us call it Fk, and then we have our capital F. So what does that mean? It means that if we have these forces resisting this, then we will have what we call the net force, which is equal to MA. So we already know the mass. So let's model this system. So we will have F minus Fc plus Fk. We say this is equal to MA. So this becomes, we can call it F of t. This will equal to MA plus, so let's keep this as the capital F. f of t will equal to ma plus fc plus fk. But what is fc? So we know that fc is actually directly proportional to velocity. So that's what we already know. That is for the damping coefficient. So this is the for the damping force. So this is going to be uh, Fc is equal to c times dx by dt, because we said the velocity is the x dt, the rate of change of displacement with respect to time. What about fk? So we shall use Hooke's law, and this is going to be k times x. Very important concepts that we must remember. Then what is the a? A is also the x2, the 2x by the t2. So substituting all of this is equation 1, and we say this is 2. So we substitute 2, put 2 in 1. So what does that mean? We shall have f of t, which will equal to m the 2x by the t2, then plus, we already have c times the x, the t, then plus kx. So this is what we have. And now what we do is to just take the Laplace. So Laplace, we are going to assume that if we assume that the x by dt at t is equal to 0, if we say that is 0, then we also assume that x is equal to 0 at t is equal to 0. In other words, the displacement has not taken place. So let us say this is in meters, this is in seconds. So if that is the case, take Laplace transform. This is equation Laplace transform both sides of equation 3. So when we take the Laplace transform, so that means I will have Laplace transform of f of t, then I will have Laplace transform of m, the 2x, the t2 plus c, the x, the t, then plus kx. So what does that mean? This becomes, I will now transform from time domain to S or complex domain. Now that means I'll have f of s, which becomes equal to m. Then we already have, let me rewrite it properly here. This will be s squared x of s. Then I add c times what? Times s x of s. Then I'm adding k times x of s. So I'm just going to factorize out. I'm going to factorize out x of s. So this becomes x of s into m s squared plus c s plus k. So that means I'm going to have, so this means I can now look for the transfer function. So the transfer function g of s equaling to f of s out of what? It is supposed to be output over input. The transfer function is the Laplace transform, Laplace of output divided by Laplace transform of input. So that means g of s must equal to we are looking at the displacement. This is displacement, and this is the input force. This is input force in S domain. This is displacement in S domain or frequency domain. So the output will be x of s divided by f of s. And if I bring this f down here and I take this side, I will have 1 out of ms squared plus cs plus k. So that is our transfer function, meaning if we substitute in now the values, it becomes a 1 out of 2s squared plus spring, the damper coefficient is given as 5, so times s, then plus the spring constant is actually given as 20, as we can check above, they were given here. So we substitute and get the transfer function. So this is basically what we need to code with the step input as we were told. So next is we needed to actually also get natural frequency of the system. So, but the natural frequency is defined as the frequency at which the system vibrates or oscillates when it is not subjected or disturbed, when it is not subjected to disturbances, oscillates when it is not subjected to any external forces or damping, or when it is not damped. It is a fundamental property of the system that depends on its mass, stiffness, and other physical characteristics. So this is how we determine it. It is omega n, and this omega n is given by square root of k out of m. So this is square root of 20 out of 2, and this is giving us approximately, or so square root of 10 is approximately equal to 3.1623 radians per second. So that is our natural frequency, because those are the model quantities. So these are called the model quantity. Next is zeta, or the damping ratio. So zeta, the symbol is funny. So our zeta is actually going to be C divided by 2 square root of mk, and this is equal to 5 divided by 2 square root of m is 2, k is 20, and this is approximately equal to 0.3953. So we know that this zeta is supposed to be between 0 and 1 for underdamping, for underdamped system. So since we have it at 0.3953 for this system, the system is underdamped. So we will have underdamped oscillations. So, but obviously, when it is above 1, then we call it overdamped. This is overdamped. So this is when we have real and distinct roots. Then when it is equal to 1, then this is critical critically damped or critical damped. So here you'll have real and equal roots or repeated roots. Then when it is equal to 0, then we say it is undamped. So the roots that we are talking about are the roots of this characteristic equation, this one. When you look for the roots for this, you realize that. Now let's look for roots of our equation of the denominator in G of S. So we have 2s squared plus 5s plus 20. So when we use the equation s equivalent to minus b plus or minus square root of b squared minus 4ac divided by what? Divided by 2a, we realize that our s is equal to negative 1.25 plus or minus j of 2.9047. So what does this gives us? This gives us what we call a stable, this gives us a stable system since we have a stable complex conjugate. Yeah, so this system is stable. In other words, it will oscillate and then return back to the steady state so fast. So here the system is underdamped. Here the system is underdamped, and let us check if how it responds. So response to step input. So we already know that x of s for a step will mean that we are getting g of s, we are multiplying it by 1 out of s. So meaning we shall have 1 out of s into 2s squared plus 5s plus 20. So what does that mean? This is what is going to happen. So we are going to use what we call the final value theorem. So the final value theorem says that if we want to determine the steady state value, want to determine the steady state value when we give it a step input. So this is going to be limit, first of all, as t tends to infinity of x of t. This is equal to when you limit s times x of s divided by, as x tends to 0. So that means we already know when we give it a step input, because we know when we give it a step input, this is what it is going to be. In other words, this is what we are saying. We have our transfer function as x of s. Remember we said this is what we are saying. X of s is equal to f of s times g of s. But we are saying f of s is 1 out of s unit. The Laplace transform of the unit step input is what? Is 1 out of s. We know the unit step input is like this. So if you have f of t equivalent to the unit step, we know that the unit step input is 1, okay? Is 1 for t greater than or equal to 0, and is 0 for t less than 0. So when you plot it on the graph, you realize that it is actually going to be something like, so it will be at 1. So when I take the Laplace transform of this 1, I will get 1 out. So that's why when we say, so this is a Laplace transform of f of t. So it will equal to the Laplace transform of 1. So when we bring it in here, then x of s becomes what? Becomes 1 out of s times g of s, which will be 1. This is 1 out of 2s squared plus 5s plus 20. So that means our x of s becomes 1 out of s into 2s squared plus 5s plus 20. This is exactly what we are saying. So using the final value theorem, so from final value theorem, then the steady state value of displacement will become what? When we displace it using a unit step input, what will be the steady state value for this transfer function? So we will have, we said we have limit x of t as t tends to infinity. Since we are no longer in the t domain, we shall use the s domain. So we limit as s tends to 0 of s times x of s. So what is x of s? We know it. So the steady state value x of xss will become limiting as s tends to 0, s times 1 out of s into 2s squared plus 5s plus 20. So meaning this will go. When we substitute in here, what will happen? The value will be 1 out of 0 plus 20. So this gives you 0.05. So steady state displacement will be xss, which will equal to 0.05. So it is now time to turn it to MATLAB. So let's go to MATLAB. So MATLAB is already open. So what I will do is to clear first of all. Then after clearing, I say CLC. I've cleared the workspace and also I've cleared also the command window. So we start. So this is called a mass damper, a mass spring damper model with the following. We said M, so we shall first clear, and then we also clear the workspace and clear the command window so that our model produces reproducible results. So we start M is equal to C, we can put them at the same level. C is equal to 5. Then we again said K is equal to 20. This is not supposed to be there. Then we go down. So what we are going to do is to now design our G, which is the G of SA. It is supposed to equal to the transfer function of what? Of 1, okay? Or we can first define the numerators. So we say the new numerator is equal to 1 according to what we have, and the denominator, let me put it also here, denominator is equal to the results that we have there is M, then we have C, then we have K. Yes, because it is 5, it is 2s squared plus 5s plus 20. So that is over. Then we say we want to use G, which is equal to the transfer function of the numerator, comma, the denominator. So that means we are designing the transfer function, which is going to be 1 out of 2s squared plus 5s plus 20. So we can go ahead. So next, since we have already given our transfer function, we can define the time domain. Or so this is going to start from 0. Let's use a step size of 0.01, and then we take it to 20. Yeah. So next is we need to define that we are giving it a step input. So let's say y, which is we can define it as x of t. This is our x of t, comma, then time out. So this is going to be like we are saying the output of this function is going to be two values. So this is giving us step of g. I hope that makes sense, but a step of g with time. Yeah, that's what is very important for us to note here. So we continue. The next is to plot. So we want to plot the values of t out. We have t out and x of t. But then we are going to format our line. So we say the line that we are using to plot should have a line width of 1.5. So we can say this is what? This is supposed to be in quotes, line width like this, then comma 1.5. So we can close it, and then we can do the grids. We say grid on. We make sure that our grids are on, and then we label. We can say this is our title of the graph. So this title is going to be step input or step response of mass. So we say this is step response of mass spring damper system. Then next we need to label. We can say x label. So the x-axis is for time. So we put time in seconds. We also have the y label. We put displacement. This is supposed to be displacement in meters. So next is we can again say we want the info, since the question was you have to display the step info. So where you give details like you need to look at the overshoot, the undershoot, and all those values at the steady state plotting. So when it rises up, what time does it take? That's the time of rise. Then you look at the overshoot, the undershoot, and all of that. So we are giving it info is equal to step info. It is supposed to be step info of our transfer function. Then next is to display. We need to display the info. So here I'm going to first of all save. So I know where to save. This is going to be the mass spring damper code. So what we do, we are going to run. When we run, is what we get. So what is the steady state? The steady state value, as we calculated, you can see we calculated it accurately as 0.05. So you will see that this is underdamped in such a way that it first overshoots beyond the steady state value, then it comes back and then stabilizes. So if you want, we can now look at the information that we are talking about. So the rise time is 0.4611 seconds. The settling time is this. The settling minimum, the overshoot is this. The undershoot is that. The peak is this in terms of displacement, and the peak time is 1.0684. The peak, you can see it from here. You can see this is 0.06 something. So that is in terms of displacement. So that's what we have. You can again check if, for example, the spring constant is actually 50. This is what happens. Let's check what happens. So you can now start varying. If you're designing, for example, a shock absorber or a suspension system, you can start testing your system to see what is going to happen. If now the numerator is like 5, let us say it is also given as a matrix as maybe 5, let's say 5, like this. So you start testing your system and see what is happening. The steady state is around this below. Okay, let's check the value here. The value is here. So the peak is at this, and the peak time is that. The overshoot, this is too big. So what we do, we go back and say, no, we don't want that. So let's see, maintain it at 4, and we see what happens to this system. So what happens to this system? The overshoot is actually reduced. Then that's how you keep adjusting these values into your system, and then you know that now when I'm going to design a spring, my spring is going to be of 50, or it's going to be of 20, it's going to be of this value, and this is how my suspension system is going to be responding. Obviously, you don't want to have a suspension system that when you hit in potholes, it vibrates forever. That's not desirable. It should vibrate a little bit, and then the vibrations die out immediately and then return steady state. So ladies and gentlemen, this is how we are able to attempt this problem and then be able to right away start from the design and up to testing in MATLAB.